In your plant, there are process conditions that can vary or change, such as temperature, pressure, flow, and level. These conditions that can change are called process variables. Frequently, these process variables have to be maintained at or near a desired value, called set point. The instruments in your plant that work together to automatically maintain a process variable at or near set point make up what is called a control system. In this program, we're going to discuss basic pneumatic control systems. We'll start by looking at the elements normally found in a basic pneumatic control system and what they do. We'll also learn about sources of information about the control systems in your plant. And we'll look at some basic pneumatic control systems used to maintain temperature, pressure, flow, and level. The principles that are discussed here about basic pneumatic control systems can be applied when you work with more complex control systems. When you work on pneumatic control systems in your plant, you'll find that they can include a wide variety of instruments, such as transmitters, recorders, controllers, gauges, actuators, and positioners. But no matter how simple or complex they are, control systems typically have four main elements. If you can identify these elements and explain what they do, then even more complex control systems will be easier to work on. To see what these four elements are and what they do, let's look at a simple illustration of a basic control system. In this illustration, this block represents a process variable. These blocks represent the four elements of the control system that work together to maintain the process variable at or near set point. The four elements include a primary element, a measuring element, a controlling element, and a final control element. The primary element is a mechanism that senses or monitors the value of the process variable. It produces a signal, usually in the form of a mechanical motion or a physical change, that represents the value of the process variable. The measuring element is a mechanism that measures the signal from the primary element and produces a pneumatic signal that represents the value of the process variable. The measuring element sends this signal to the controlling element. The controlling element is a mechanism that generally performs four functions. It measures the signal from the measuring element, compares the measured value to set point, computes the difference between the measured value and set point, and produces a pneumatic signal that is used to correct any difference between the measured value and set point. The controlling element sends its signal to the final control element. The final control element is a mechanism that converts the signal from the controlling element to a corrective action that affects the process variable and returns it to or keeps it near set point. So, the four elements normally found in a control system are a primary, measuring, controlling, and final control element. Now, the four elements of a control system are typically arranged in one of two different ways. The two basic arrangements are a feedback control system and a feed-forward control system. Now, let's talk about the feedback control system first. Feedback is a system arrangement in which the system continuously monitors and measures the value of a process variable, compares this value to set point, and takes corrective action to return the process variable to or near set point. To see how this is done, let's look at a simple illustration of a feedback control system. In this illustration, these blocks represent the four elements normally found in most control systems: the primary element, the measuring element, the controlling element, and the final control element. This block represents a process with a process variable which the control system has to maintain at or near set point. This line represents a pipe that supplies material to the process, which we'll call the supply. This line represents a pipe that takes material from the process, which we'll call demand. As long as the supply and the demand are equal, the process variable should not change. But if the demand changes and the supply doesn't, the process variable will change. Well, let's see how the feedback control system would respond to this change. The primary element in this system continuously monitors the value of the process variable and provides a signal to the measuring element. The measuring element continuously measures the value of the process variable and produces an output signal that is sent to the controlling element. The controlling element compares the signal from the measuring element to set point and produces an output signal which it sends to the final control element. And the final control element changes the signal to a corrective action. Here, the corrective action manipulates or adjusts the supply. Because a feedback system continually monitors and measures the value of the process variable, the value of the process variable is fed back into the control system so that the system continues to provide a corrective action until the process variable returns to or near set point. The major advantage of feedback control is that since the control system continuously monitors the process variable, it always knows what the value of the process variable is and is able to continuously provide corrective action that maintains the process variable at or near set point. The major disadvantage of feedback control is that the process variable has to change before the control system responds to correct it. Now, you may recall that I said we'd look at two control system arrangements. Feedback was one, and the other is feed forward. Feed forward is a system arrangement in which the system continuously monitors and measures the value of a variable that, if not corrected, would cause the process variable to change. The feed forward system compares this measured value to set point and takes action to prevent the process variable from changing. So to see how this is done, let's go back to our simple feedback illustration. Here's the illustration of the control system that we just looked at. Without changing any of the elements in the control system, we can move the primary element so that it monitors the value of the demand rather than the process variable. With this simple change, the control system is now a feed-forward control system. Now, you may recall that in this process, if the demand changes so that the demand and the supply are not equal, the process variable will change unless the supply is changed. However, the feed-forward control system takes action to manipulate the supply so that it balances the demand change before the process variable can change. So, a feed-forward control system measures the variable that would cause the process variable to change and responds by manipulating another variable before the process variable can change. The disadvantage is that since the process variable itself is not being monitored, if the process variable were to change, the control system would not be able to detect or correct the change. Now, the two control system arrangements that we looked at, feedback and feed-forward, were very similar. Both included the four elements typically found in a control system, and both monitored one variable and manipulated another variable in order to maintain a process variable at or near set point. But the feedback and feed-forward arrangements were also different. Feedback works to correct changes in a process variable, and feed-forward works to prevent the process variable from changing. By identifying these similarities and differences between the control systems in your plant, you may find that even complex control systems are easier to work on. Most plants have diagrams and text material that you can go to help you learn more about your plant systems and make it easier for you to work on them. In the next part of this program, we'll look at some of these sources and the kinds of information that you can get from each of them. But before continuing, review the first section of your text. Most plants have a variety of sources that you can refer to when you need information about the equipment, instruments, and systems in the plant. You may be familiar with some of these sources, which can include piping and instrumentation diagrams, control logic diagrams, plant data books, manufacturers' instrument service manuals, instrument calibration records, and of course, other experienced technicians and operators. In this part of the program, we're going to look at piping and instrumentation diagrams and control logic diagrams, sources that you may refer to often for information about the control systems in your plant. What we'll be looking for is the kind of information that you can get from each of the diagrams. Well, let's start by taking a look at a typical piping and instrumentation diagram. A piping and instrumentation diagram is often called a P&ID. As you may know, a P&ID is a fairly detailed diagram of the process systems and associated control systems in a plant. It can include symbols and information that allow you to identify major pieces of equipment, the piping that connects the equipment, piping sizes, control instruments, and instrument tubing. Usually, there's a lot of other information that's in a P&ID. Some of it has to do with control systems and some of it doesn't. Now, we're not going to try to identify all the kinds of information that you can get from a P&ID because right now we're only interested in the control system information it may contain, such as what instruments are in a given control system and how the control system relates to process systems. To see how you can get this information, let's look at a simplified illustration of a portion of a P&ID. In a P&ID, control system instruments are generally identified by circles, and the circles usually contain letters and numbers that identify the instrument and the system it is in. The letters used to identify the instruments are pretty standard, and they usually have specific meanings. The first letter normally identifies the process, such as L for level, T for temperature, P for pressure, and so on. The second letter normally identifies the function of the instrument, such as T for transmitter, or C for controller. Symbols that contain more than two letters often represent instruments that have more than one function. For example, the I here identifies an indicating function. So this instrument is a level indicating transmitter. Now, although the letters and symbols used in P&IDs are generally standard, there can be some variations from plant to plant. So most plants normally have a chart called a legend at the beginning of the plant's diagrams. The meanings of the letters would typically be identified in the legend. The instrument symbols in a P&ID also often include numbers. These numbers have specific meanings as well. Let's look at our simplified P&ID to see what the numbers are for. The first numbers in the instrument symbol typically identify the control system that the instrument is in. For example, the number 20 here identifies this level transmitter as being part of control system number 20. All instruments that are part of this control system will be identified by the same first numbers, 20. The last numbers typically identify the particular instrument in the control system. For example, the 01 identifies this level transmitter as the first instrument in the control system. If the transmitter were the 11th instrument in the system, it would be identified with the numbers 11. Now, we can look at each of the instrument symbols in this simplified P&ID and identify what each instrument is. We already know that this is a level transmitter. It's in control system number 20, and it's the first instrument in the system. This is a level controller. It's also in control system number 20, and it's the second instrument in the system. And this is a level control valve, also in control system 20, and the third instrument in the control system. Since all of the instruments in this control system perform functions for the same process variable, level, this means that this is a level control system. The lines that connect the instruments to each other and to other components tell us how the different parts of the systems relate to each other. For example, lines with hash marks are standard indications for pneumatic signals. So these instruments send pneumatic signals through the control system. A solid line indicates a connection, such as piping to a process. Frequently, arrows may be included to indicate the direction of flow of some fluid. Here, the diagram indicates that fluid is flowing to a tank. And here, fluid is flowing from the tank. A solid line also connects the tank to the transmitter. So, the transmitter is monitoring and measuring level in the tank. Here, the level control valve is included in the line that supplies fluid to the tank. This tells us that the valve is used to manipulate the flow of fluid to the tank. So, from a simplified example of a P&ID, we were able to determine some general information about a pneumatic control system. We identified the instruments in the system, and we learned that the transmitter is monitoring level in a tank, and that the control valve is manipulating flow into the tank. Overall, control system information like this is useful to you for a number of jobs that you may have to do as an instrument technician. For example, if a control system is acting up and you have to find out what's wrong, a P&ID helps you identify the main instruments in the control system and generally what they do, so that you can begin to trace down the problem. But suppose you need specific information about how a particular instrument works in a given control system. Now, this kind of information can often be found in a control logic diagram. A control logic diagram is a diagram of the instruments in a specific control system. The instruments are generally represented by standard symbols. For example, in a control logic diagram, a circle represents a measuring or readout instrument. Here, these letters and numbers identify the measuring instrument as the same level transmitter that we identified in our simplified P&ID. A rectangle is used for instruments that process signals automatically. Again, these letters and numbers identify this instrument as our level controller. A trapezoid represents a final control instrument, identified here as the control valve in our level control system. Frequently, symbols inside the standard instrument symbol shape will identify additional information about the instrument it represents. For example, a rectangle representing a controller will often have a symbol that identifies the function that the controller performs. This symbol indicates that the level controller performs a proportional function. You may recall that a proportional controller produces a change in output that is proportional to any change in input to the controller. A controller symbol may also contain information that identifies input and output ports or connections. The label E2 identifies the input port for this controller. Sometimes identifying the input port is extremely important. For example, in this controller, E2 is the input used to make the controller reverse acting, which means that when the input to the controller increases, the controller will produce an output that decreases. An E1 input is often used to make the controller direct acting, which means when the input increases, the controller increases its output. The O usually represents the output port. There are a wide variety of standard symbols that can be used inside the instrument symbols in a control logic diagram. And like the legend for a PNID, a legend is frequently included at the front of control logic diagrams in most plants. Now, sometimes a control logic diagram will include information relating to the specific operation of instruments in a system. Let's look at some examples in the diagram we've been looking at. This additional information is usually off to one side of the instrument symbol that it relates to. For example, this information tells us that the level transmitter will measure a level range of 0 to 32 inches of water, and that the normal measurement, or set point, is 16 inches. In addition, when the transmitter measures the normal level, its pneumatic output signal is 9 psi. This information gives the input-output range for the level controller. According to this information, when the input to the controller is 8 psi, the controller will produce an output of 3 psi. And when the input is 3 psi, the output will be 15 psi. The gain setting for this controller is 2.4. This means that when the input to the controller changes by 1 psi, the output will change by 2.4 psi. Next to the symbol for the control valve, the diagram indicates that the valve is closed when the signal it gets from the controller is 3 psi, and the valve is open when the signal is 15 psi. If you look at the information for each instrument separately, it only tells you how that specific instrument operates. But if you look at how the information interrelates, you can determine how the instruments work together as a system. For example, if a 9 psi signal from the transmitter represents a normal level, and the controller changes its output only when the input signal changes between 8 and 3 psi, then the controller will only change its output when the transmitter sends a signal indicating a level that is below normal. From the information in this diagram, we can also determine that when the input decreases from 8 psi to 3 psi, indicating a decreasing level, the controller output increases from 3 psi to 15 psi. An increasing controller output signal causes the valve to open. Essentially, for the control system we looked at, when the transmitter senses that the level is dropping, it triggers a control response that opens the valve to allow more fluid into the tank in order to maintain the level in the tank. So a PNID provides an overall picture of what the main instruments are in a control system and how the system relates to process systems. And a control logic diagram provides specific information about the individual instruments in a control system that helps you determine how the instruments work together as a system. Both are important sources of control system information that you should become familiar with. Take some time now to review the material in your text on sources of control system information. When you return, we'll look at a basic pneumatic control system that maintains temperature. In this part of the program, we're going to look at a basic pneumatic control system that maintains temperature at set point. First, we'll look at a simple process system. Then we'll see how a basic pneumatic control system maintains temperature in the process. And finally, we'll discuss how the control system is set up to compensate for characteristics of the process. Let's begin by looking at a simplified illustration of a heat exchange system. In this system, cooling water is circulated through plant equipment in order to cool the equipment. As the cooling water cools the equipment, the water becomes heated. The heated cooling water flows to a heat exchanger and is circulated around a bundle of tubes inside the heat exchanger. Water from a river, called raw water, flows through the heat exchanger tubes and reduces the temperature of the cooling water that flows around the tubes. Now, a control system is needed in the heat exchange process that will keep the temperature of the cooling water at a desired value, or set point. The way the cooling water temperature is maintained is by controlling the raw water flow through the heat exchanger tubes. Let's look at the basic pneumatic control system that can maintain the cooling water temperature at set point automatically. The primary element in this system is a temperature sensing bulb and capillary tube that are connected to a sensing mechanism inside the transmitter. The measuring element is another mechanism inside the transmitter. The controlling element is this controller. And the final control element is a positioner and actuator that operates a valve in this pipe. In this system, the elements work together to maintain cooling water temperature at a desired value. Now, assume that the cooling water temperature is at set point. Let's see how the control system maintains cooling water temperature. The transmitter continuously monitors and measures the temperature of the cooling water and produces a pneumatic signal that represents the cooling water temperature. The transmitter sends the signal to the controller. The controller measures the input signal, compares it to set point, computes the difference between the input signal and set point, and produces a pneumatic output signal, which it sends to the final control element. If the cooling water temperature is at set point, the controller computes no difference between the input signal from the transmitter and set point. And the signal that the controller sends to the final control element keeps the valve at its present position. Since the valve doesn't move, raw water flow through the heat exchanger tubes stays the same. However, if the cooling water temperature changes for any reason, the transmitter senses and measures the change and produces a pneumatic output signal that represents the changing temperature. This time, the controller will compute a difference between the input signal and set point and changes its output signal to represent this difference. The new controller output adjusts the valve to increase or decrease the flow of raw water through the heat exchanger tubes and change the temperature of the cooling water. The transmitter continues to sense the temperature as it changes and feeds back a signal through the control system to manipulate raw water flow until the cooling water temperature returns to set point. So in general, a basic control system monitors a variable and responds to changes by manipulating another variable to maintain temperature at set point. However, as you probably know, the specific response of a control system is affected by process characteristics such as capacitance, resistance, and dead time. Let's define each of these characteristics and relate them to our heat exchange process. Capacitance is the ability of a material to store energy. An example of capacitance in our heat exchange system is the ability of the cooling water to store energy in the form of heat. Now, the heat exchange system has a lot of cooling water, and the water has the capacity to store a lot of heat. The capacity of a large amount of water to store a lot of heat means two things to us as far as the control system is concerned. One is that the water won't heat up very fast, so the control system will not have to respond quickly to keep the cooling water temperature from increasing out of control. By the same token, the cooling water temperature will not come down very fast, So corrective action from the control system will generally return the temperature to set point slowly. So capacitance has an effect on the response of the control system. We'll look at what is done to compensate for capacitance in a couple of minutes, but right now let's look at the characteristic called resistance. Resistance is the ability of a material to resist the flow of energy. This is a cross-section of one of the tubes in our heat exchanger. The metal of the heat exchanger tubes resists the flow of heat from the cooling water through the walls of the tubes and to the raw water in the tubes. This resistance slows down the flow of heat from the cooling water, and like the capacitance of the cooling water, causes the cooling water temperature to change slowly. The last characteristic we're going to look at is dead time. A dead time is the time that it takes for energy to flow from one point to another. In this heat exchange system, dead time is the time it takes for a change in the amount of heat produced by the plant equipment to be sensed as a change in cooling water temperature by the sensing element. The dead time results in a delay between the time the cooling water temperature begins to change at the equipment and the time the control system senses and responds to the change. The combined effect of the capacitance, resistance, and dead time in the heat exchange process is that cooling water temperature changes slowly. Now, generally, the controller in a control system is adjusted to compensate for the characteristics of the process. If we look at the control logic diagram for our temperature control system, we will see how the controller is adjusted for this particular system. These symbols indicate that the controller used in this system is a proportional plus integral controller. As you may know, this means that the system is designed to bring temperature back to set point. This information tells us how the controller is adjusted. The controller is set for a gain of 1. A gain of 1 means that with a 1 psi input change, the controller will change its output 1 psi. The controller is also set for an integral of 0.5 repeats per minute, which means that the controller will repeat half of its proportional output every minute, for as long as the temperature is away from set point. What these gain and integral settings mean is that as temperature slowly changes away from set point, the response from the control system will not be very dramatic. The response will merely be enough to compensate for the characteristics of the process and return temperature back to set point. Now, in this part of the program, we've looked at a control system that monitors one variable and manipulates another variable in order to maintain temperature at set point. And we looked at how the controller was set up to compensate for the characteristics of the process. In the next part of this program, we'll look at a basic control system that maintains pressure at set point. But first, review the material in your text on temperature control systems. Be sure to discuss any questions you may have with your instructor. In this part of the program, we're going to look at a basic pneumatic control system that maintains pressure at set point. You'll find that the control system is very similar to the system we looked at that maintained cooling water temperature. Our approach will be the same as for the temperature control system. First, we'll look at a simple process system. Then we'll see how a basic pneumatic control system maintains pressure in the process. And finally, we'll discuss how the control system is set up to compensate for the characteristics of the process. The process system example we're going to look at is part of a fuel oil supply system. This part of the illustration represents a header. A header, in this example, is a pipe that has smaller pipes branching out from it. In essence, the header in this example is a supply pipe for a number of other pipes. In this system, fuel oil is supplied to the header, which distributes it to burners in a boiler through the smaller pipes. The process variable that has to be maintained in this system is pressure in the header. header pressure has to be kept at a constant value so that the flow of fuel oil from the header remains constant. As long as the amount of fuel oil supplied to the header is balanced with the demand for fuel oil from the header, the pressure in the header will not change. Now, when the demand for fuel oil changes, pressure in the header will change. And the way the pressure is returned to set point is by controlling the amount of fuel oil that flows to the header. Let's go ahead now and look at a control system that monitors header pressure and manipulates the supply of fuel oil to the header in order to maintain pressure at set point automatically. Pressure in the header is conveyed through this line to a transmitter. This transmitter contains two of the elements in this control system, the primary element and the measuring element. The controller is the controlling element for this system. And the final control element is a positioner and actuator that operates a valve in the supply line. Now let's see how these elements work together to maintain pressure in the header. Suppose the demand for fuel oil changes. Since fuel oil supply is not equal to the demand, header pressure changes. As the pressure changes, the transmitter senses the change, measures it, and sends a representative pneumatic signal to the controller. The controller measures the signal, compares it to set point, computes the difference, and produces a corrective signal that it sends to the final control element. The final control element responds by moving the valve to change the amount of fuel oil that flows to the header, which in turn changes the pressure in the header. The transmitter continues to monitor header pressure and feed back a signal through the control system to manipulate the flow of fuel oil to the header until the header pressure returns to set point. The control system that we just looked at is very much like the control system that we looked at that maintained cooling water temperature. Both basic control systems monitored one variable and manipulated another variable in order to maintain a process variable at set point. Now, as we learned earlier, the specific response of a control system is affected by characteristics of its related process. You may recall that the characteristics of the temperature system were such that temperature changed slowly, and that the controller was set up to compensate for the characteristics. Well, in the fuel oil supply system, the characteristics are such that pressure changes very fast. So when the demand for fuel oil changes, the pressure in the header will change very quickly. By the same token, when the control system manipulates flow of fuel oil to the header, this control action will cause the pressure to change quickly as well. Well, let's go to the control logic diagram for the pressure control system to see what controller settings are used to compensate for the characteristics of the process. Now, here we can see that this controller is a proportional plus integral controller, which we could have expected since the system returned pressure to set point. This controller also has a gain setting of 1 and an integral setting of 0.5 repeats per minute. Well, now wait a minute. First, we looked at a process with characteristics that caused temperature to change slowly, and the controller was set for a gain of 1 and an integral of 0.5. Well, now we're looking at a process with characteristics that cause pressure to change quickly, and the controller has the same settings as the controller for the temperature system. But because of the different process characteristics, the response of each control system is different, even though the controllers are adjusted the same. In the heat exchange process, a small change in the output of the temperature controller causes slow changes in temperature. This slow response is enough to keep the temperature from increasing or decreasing out of control and to return it to set point. In the fuel oil process, a small change in the output of the pressure controller causes rapid changes in pressure. This rapid response is enough to keep the pressure from increasing or decreasing out of control and return it to set point. So the temperature and pressure controllers each compensate for the characteristics of their related processes. and they do it with the same settings. Now, this doesn't mean that all controllers are going to be adjusted for a gain of 1 and an integral of 0.5. In the next part of the program, we're going to look at a basic flow control system. And as you'll see, its controller will be adjusted quite differently from the temperature and pressure controller settings that we looked at. We'll move on to the flow control system after you review the material in your text on pressure control systems. So far, we've looked at two basic pneumatic control systems. One maintained temperature at set point, and the other maintained pressure at set point. And each of the control systems were adjusted to compensate for the characteristics of its related process. In this part of the program, we're going to look at a basic pneumatic control system that maintains flow above set point. Again, we'll start by looking at a simple process. Then we'll see how a basic pneumatic control system maintains flow in the process. Finally, we'll discuss how this system is set up to compensate for the characteristics of the process. Let's go to the simplified illustration of the process system. This illustration represents part of a condensate flow system. In this system, a pump takes suction or draws condensate from a tank and discharges the condensate through a pipe. If the plant demand for condensate changes, flow through the discharge pipe changes, and flow through the pump changes. Now, the variable that has to be maintained in this process is flow through the pump. Flow through the pump has to be kept above a given value to keep the pump from overheating. So when the demand for condensate decreases, causing the flow to drop below the given value or set point, a valve is opened in this pipe to recirculate the condensate back to the tank. Recirculating condensate to the tank allows condensate to continue to flow through the pump at some value above set point and prevents the pump from overheating. Now, an important thing to remember is that in this process, flow has to be kept above set point rather than at set point. It doesn't really matter what the flow is as long as it's above set point. So with that in mind, let's look at the control system for this process. As in the pressure control system, the transmitter in this system contains two of the four elements normally found in a control system: the primary element and the measuring element. Again, the controlling element is the controller, and the final control element is a positioner and actuator that operates a valve in the recirculation line. Let's see how this flow control system works. In this system, the transmitter monitors and measures values representing flow through the discharge line. We know that if flow through the discharge line changes, that flow through the pump will change as well, although we don't know exactly what the flow is through the pump because the control system is not monitoring flow through the pump. So suppose the demand for condensate changes and the discharge flow drops below set point. The transmitter senses the change, measures it, and sends a representative pneumatic signal to the controller. The controller measures the signal, compares it to set point, computes the difference, and produces a corrective signal that it sends to the final control element. The final control element responds by opening the valve. This recirculates some of the condensate back to the tank to ensure that condensate flow through the pump increases above set point. Since the transmitter is monitoring demand, the control system doesn't respond to this increase in flow through the pump. But when the demand for condensate changes again and discharge flow increases above set point, the control system responds by shutting off the flow of condensate through the recirculation line so that the full discharge from the pump goes to satisfy the demand in the plant. So essentially, when the discharge flow drops below set point, the control system opens the valve in the recirculation line. And when the discharge flow increases above set point, the control system closes the valve. As before, the response of the control system is affected by the characteristics of the process. In the condensate flow process, the characteristics are such that flow can change very quickly. So a small change in the output of the controller will cause a rapid change in flow. But in this particular process, it's not enough for the control system to respond quickly to compensate for rapid flow changes. If flow through the discharge line drops below set point, the control system also has to make sure that flow through the pump changes a lot, so that there's no chance that the pump could overheat. Let's take a look at the control logic diagram for our level control system to see how the controller is adjusted to provide a quick and drastic response. The controller in this control system is a proportional-only controller. Integral is not needed because flow does not have to be kept at set point, only above set point. The gain setting is 6. A gain of 6 means that when the input to the controller changes 1 psi, the controller will change its output 6 psi. So a small change in the discharge flow below set point will result in a large change in the controller output. This in turn opens the valve most of the way and ensures that the flow through the pump is more than enough to keep the pump from overheating. Now, so far we've looked at basic temperature, pressure, and flow control systems. The temperature, pressure, and flow control systems in your plant may or may not provide the responses we discussed in our examples. The response of your control systems will depend, of course, on the characteristics of the process it's associated with. In addition, the control systems in your plant are not always going to look as simple as the ones we've looked at. In the last part of this program, we're going to look at a level control system. It will seem quite a bit different from the basic systems we've seen so far. But as we'll see, control systems are really all about the same, regardless of how they appear. We'll look at the level control system after you take some time to review the portion of your text on flow control systems. In this last part of the program, we're going to look at a control system that maintains level within a fixed range. As we'll see, this system is just a little different from the other systems we've looked at, but the basics still apply. Let's begin, as we have before, by looking at a simplified illustration of a process system. This illustration represents part of a condensate system. In the system, steam that has been used in the plant is directed into a condenser, where steam is condensed into water, or condensate. The water collects in a hot well, which is this tank located below the condenser. 2 pumps draw water out of the hot well and pump it to various processes in the plant. Now, in this system, the variable that has to be maintained is water level in the hot well. If the amount of water entering the hot well is balanced with the demand for water from the hot well, the level in the hot well will not change. But if the amount of the water entering the hot well is greater than the demand, the level in the hot well will gradually increase. When the level rises to a predetermined point, a valve starts to open in this pipe called the draw-off line to drain off the excess water and keep the level from rising any further. On the other hand, if the amount of water entering the hot well is less than the demand, the level in the hot well will gradually decrease. When the level drops to a predetermined point, a valve starts to open in this pipe called the makeup line to allow water from other sources to flow into the hot well and keep the level from dropping any further. So, condensate level in the hot well has to be kept from getting too low or too high. Let's look at the control system that maintains the water level in the hot well automatically. This illustration is a close-up view of the system we just looked at. This part of the illustration represents the hot well. Here's the draw-off line and the makeup line. The primary element for the control system is a displacer. The measuring element is this transmitter. This control system has 2 controlling elements, which are these 2 controllers. And this control system also has 2 final control elements, which are the actuators and positioners that operate valves in these pipes. Let's briefly look at how the elements in this control system work together to maintain water level in the hot well. As the water level in the hot well changes, the displacer senses the change and converts it into a mechanical motion. The transmitter measures the motion from the displacer and produces a proportional pneumatic signal that represents water level. It sends this signal to both controllers. When the transmitter produces a signal that represents a high water level, this controller produces a corrective signal that opens this valve to drain off the excess water in the hot well and keep the water level from rising any farther. When the transmitter produces a signal that represents a low water level, this controller produces a corrective signal that opens this valve to add water to the hot well and keep the water level from dropping any further. So our level control system example has two controlling elements and two final control elements. Additional control elements can sometimes make a control system appear more complex than it really is. But identifying the main elements of the control system and what they do make it easier to understand the system. Now, the characteristics of our level system are such that level changes slowly, and we can expect that the controllers are adjusted to compensate for the process characteristics. As before, we can identify the controller settings by looking at the control logic diagram. However, since the level control system is more elaborate than the other systems we've looked at, we can get a clearer picture of how the level system works by looking at all of the information on the control logic diagram. So let's go to the control logic diagram for our level system and see what we can learn about the system that will make it seem less complex. Let's start with the transmitter. This information next to the transmitter symbol indicates that the transmitter can measure a level range in the hot well of 0 to 32 inches of water. A water level of 16 inches is normal. The 9 psi means that with a normal level of 16 inches in the hot well, the transmitter will produce a pneumatic signal of 9 psi. Both controllers are proportional controllers. In this level system, proportional control will keep the level within a fixed range, but it may not return the level to set point. The data next to this controller symbol specifies the controller input and output signal ranges and the controller gain setting. Here, the input signal range is 10 to 15 psi, and the output range for this controller is 3 to 15 psi. This means that when the input to the controller is 10 psi, the controller will produce its minimum output. And when the input is 15 psi, the controller will produce its maximum output. In other words, the controller only responds to input signals between 10 and 15 psi. So if the normal signal to the controller is 9 psi, this controller will only change its output when it receives a signal indicating a water level above normal, or in other words, above 9 psi. In addition, for this controller, an input change of 5 psi from 10 to 15 results in an output change of 12 psi from 3 to 15. This gain setting of 2.4 accounts for the proportionally larger output change in relation to a smaller input change. The controller output manipulates the valve in the draw-off line. This information shows that with a 3 psi signal from the controller, the valve is closed, and with a 15 psi signal, the valve is open. Essentially, what we've looked at so far in the control logic diagram is one simple control system, and that's a system that opens a valve in the draw-off line when water level in the hot well rises above normal. But that's not the whole system. So let's go back to the diagram and look at the other half of the system. For this controller, the input signal range is 8 to 3 psi, and the output is 3 to 15 psi. When the input to the controller is 8 psi, the controller will produce its minimum output. And when the input is 3 psi, the controller will produce its maximum output. This means that this controller only responds to input signals between 8 and 3 psi. Or in other words, this controller will only change its output when the transmitter sends a signal indicating a water level below normal, which, as you may recall, is 9 psi. So for this controller, an input change of 5 psi from 8 to 3 results in an output change of 12 psi from 3 to 15. As with the other controller, the proportionally larger output is a result of a gain setting of 2.4. The output from this controller manipulates the valve in the makeup line. Like the other valve, this one is closed at 3 psi and open at 15 psi. So by looking at this control logic diagram to see how the level control system works, we learned that essentially the level control system is two simple control systems that have been combined by using one common transmitter. One of the systems works to open a valve in the draw-off line when water level in the hot well rises above normal. The other opens a valve in the makeup line when the water level drops below normal. The level control system that we just looked at was different from the basic temperature, pressure, and flow control systems that we looked at earlier. It used two controllers and two final control elements in order to maintain level. Now, in your plant, you may find control systems with any number of combinations of instruments. Some systems may have several transmitters sending signals to one or more controllers. Or you may find a system where the output from one controller may go to another controller. The variety of pneumatic control systems is almost limitless. However, the basics still apply. Control systems, regardless of how they appear, will normally have a primary element, a measuring element, a controlling element, and a final control element. And the control system will monitor and manipulate variables in order to maintain a process variable at or near set point. When you work on the systems in your plant, look for the basics and use the resources available to you. And you may find that even the most complex control systems will be easier to understand and to work on.